Okay, what I thought I would do is take a couple of problems from each of those worksheets that I've put on Canvas and make a little video to discuss how to work them and the important parts of each problem. Now, what I will do in this video down below where the details are is I'll put a timestamp so that if you don't want to do section 2.3, you can skip it and go immediately to where section 2.4 starts, etc. Or you can just watch the whole thing. So on the screen is a couple of problems from section 2.1 from the 2.1 worksheet. And the first problem, you have a piecewise defined function and you're asked to evaluate f of 0. Well, you got to figure out where 0 lives. 0 is less than 5, so you're up on this branch. So you just want to plug 0 in for x, and this will be minus 3 cubed, or minus 27. Now for f evaluated at 7, 7's bigger than 5, so this will just be 1 over 7. You'll be on this branch here. Now, problem 2, evaluate g of 3. Well, we simply just plug 3 in for x. This will be square root of 16 minus 3 squared, square root of 16 minus 9, so just the square root of 7. Now, g evaluated at a, remember, this is simply a set of instructions. This means everywhere in the function g, wherever you have in function g and x, you're going to plug in a. So this is just going to be 16 minus a squared. Now this part, given function g, what is its domain? Well, we can't take a square root of a negative, so it must be the case that 16 minus x squared is greater than or equal to 0. Okay, and then we're going to use a process of elimination. This factors as 4 minus x times 4 plus x is greater than or equal to 0. Now, we're just going to draw what your textbook calls a sign chart. It's just a number line. Now, notice that when x is 4, that expression is 0. And from here, when x is minus 4, that expression is 0. If you pick any other x value and plug in to this expression, you'll get something that's not 0, either plus or minus. So let's pick a number. Let's pick minus 10. 4 minus a minus 10 is positive. Okay? And then this will be 4 plus a negative 10. That's negative, and the product is negative. So we'll just put a minus sign there. Now let's pick a number between minus 4 and 4, 0. If you plug 0 in for x, you get 16, and 16 is positive. Now pick a number bigger than 4, like 8. And then we'll have 4 minus 8 times 4 plus 8. 4 minus 8 is negative, 4 plus 8 is positive, so the product is negative. Now the question was, what numbers can I plug in and get greater than or equal to 0? Well, that's going to be where the plus sign is and where the zeros are. So the domain would be the interval from minus 4 to plus 4. That's the domain. Okay, and that'll do it for section 2.1. Pretty basic stuff. I've changed my mind. I'd like to do one more problem from section 2.1. And this problem says find the difference quotient for this given function. Now, we discussed this in class. This is nothing more than the slope of a line connecting 2 points on this curve, 2 different points on this curve, separated by an interval 8 units long on the x-axis. So, I'd bet money there's going to be one like this on the exam, so let's cover this thoroughly. Now, let's take this, first things first, let's draw this and put h down here. We need to know what this is. F of a plus h. That means everywhere you have an x in the function f, you're going to put a plus h. So this is going to be 3 times a plus h squared minus 5 times a plus h plus 9. Minus now, f evaluated at a, that means everywhere you have an x, put an a. So this is 3a squared minus 5a plus 9. Now, very important, you must have these parentheses. Without these parentheses, the correct answer is not possible. Now, once you get everything in the correct position like this, there's just going to be a lot of algebra. So let's just go through this. I'm going to have 3 times a plus h squared. Well, we know how to do this. You square the first term, you square the last term. And then the middle term is going to be this times 2. So we'll get a 2ah. Then we'll have minus 5a minus 5h plus 9 minus 3a squared minus 5a, plus 5a, right? Minus a minus plus 5a, and then minus 9. Let's check that. Minus a minus is plus, and then minus there. So this is all over h. Now, if you paid attention in class, you know what must happen. If we do the algebra correctly, we're going to be able to cancel this h down here. So let's go ahead and multiply 3 by the 3. That gives us 3a squared, 6a times h, 3h squared, minus 5a, minus 5h, plus 9, minus 3a squared, plus 5a, minus 9. All over h. Now what has to happen if I've done everything correctly? Every term without an h has got to subtract out. And maybe even some of them with an h will subtract out. We'll just see. But notice this term subtracts out. That's got an h, that's got an h. Let's go to this one. I've got negative 5a plus 5a, positive 9 minus 9. Every remaining term has an h as part of it. Okay, now in the numerator upstairs, we can factor this h out. Now everything's factored. This cancels, and we get our result. The answer is 6a plus 3h minus 5. Okay, now that will do it for section 2.1. But take note, follow all the steps in this. There's going to be one like this on the exam. I would bet money on it. Okay, now on to section 2.2. All right, here's the worksheet for section 2 of chapter 2. And let's just pick a couple of these problems and work them. We definitely want to pick the piecewise defined function. And let's pick the first one. Now it says find the x-intercepts, the y-intercepts, and then sketch a graph of the function. Well, remember, always just draw your little coordinate system here. And I like to start with the y-intercept. Wherever the curve cuts the y-intercept, what happens? Well, x must be 0, and whatever the y value is. So if we let x equal 0, we get that the y-intercept is going to be at 0, 7, right? Just let x equal 0. Now what happens at an x-intercept? Well, you get some x value, but anywhere along the x-axis, y is 0. So if I set y equals 0, I get 0 equals 7 minus x squared, or x squared equals 7. So x would equal plus or minus the square root of 7. So that means I have a minus square root of 7, 0, and a plus square root of 7, 0 as x-intercepts. So we'll just call them here. So this is minus square root of 7, 0, plus square root of 7, 0. And now, skipping ahead, looking to a further section, this is just the curve y equals x squared, which, remember, was a reference curve like that. And remember what the minus here does. It reflects it so that it opens down, and then this moves everything 7 units up. So let's just do that. And we know we're going to get a sketch like that. Okay? Not bad. Pretty basic. Pretty basic. Let's do 3. I like 3. Let's do 3. Because look at this. We recognize this as the reference curve y equals x squared that looks like that. But it shifted 3 units to the right and then 4 units down. Remember that? So if I say this is 3 and then this is 4 units down, it's going to be that curve right there. It's going to be our old friend, our reference curve, shifted 3 right and 4 down. Now let's go through the procedure. Again, look back up here. What happens at a y-intercept? Well, then x is 0. If I plug 0 in for x, I get negative 3 squared, which is 9. 9 minus 4 is 5. So it's going to cross the y-axis up here at 5. So we're going to get 0, 5 as a y-intercept. X-intercept, well, at the x-intercepts again, y is 0. So if I put a 0 here, then that's going to give me x minus 3 squared is equal to 4. Now take the square roots and I get x minus 3 is plus or minus 2. So that means then that x is equal to 3 plus or minus 2. Now this is 2 numbers, isn't it? It's 3 plus 2, which is 5. And then it's 3 minus 2, which is 1. So that means I'm going to have an x-intercept out here at 5 and 0. And then another x-intercept here at 1 and 0. Let's label it like that. And then we know what the curve is. It's our reference curve y equals x squared that was shifted 3 units to the right and 4 units down. Okay, let's go to the piecewise defined function and see what happens. In this one, everything's happening at 2. So let's say 2 is right there. After all, it says up here in the direction sketch. So this isn't going to be the Mona Lisa. This is going to be a sketch. And whoever did this wasn't even kind enough to label the x and y axis. But we can manage. So what's going on? If x is less than or equal to 2, then the curve is y equals x squared minus 4. And we know what that is. It's our reference curve shifted 4 units straight down. So that means here's the reference curve, like right here. So we would shift it 4 units straight down. So it's going to be like this. And furthermore, we'll take a peek here, see what's happening at 2. If I plug 2 in, I get y is 0. So this is also going to be a y-intercept. So I know this is going to go like that. Now that contains equals, see that? So there will be a dot here. Now furthermore, if you look at this, we see that minus 2 makes this 0. So this thing goes like this, at least this top branch. Now what about the bottom branch? Well, plug 2 in. You get 5. This is going to be the branch y equals 5x minus 10. If we just plug 2 in, we get 10 minus 10 is 0. So that means the first point on this branch is going to begin right at where this one ends. And then this we recognize as a straight line. It has slope 5 and y-intercept minus 10. So we would go 5 units up and 1 over. So we would just get some sort of straight line like that. So that would be a very rough sketch of that piecewise defined function. It's just an accident that this one starts right where the top branch ends. Happens sometimes. Let's see if there's anything on page 2 that is of interest to us from section 2. We got more piecewise defined functions. What do you say we pick on the one that looks the toughest? I can handle that. Now, in this one, stuff is happening at -3 and +3. So let's say that this is -3 and this is roughly +3. And let's just take them one at a time. If x is less than -3, then we have y equals -5. We'll call this y equals -5. There is no equals in this, so we draw a little circle. And then remember, y equals a constant, it's a horizontal line. Now what's happening between 3 and -3? Well, then this branch is y equals 5 over 3x. Notice that it passes through the origin because when x is 0, y is 0. Now that means if we go 5 units up and 3 units over, that's the slope. 5 units up and 3 units over. So look what happens here if I start at -3 at x equals -3. This is going to be y equals 5/3 times -3. Those cancel, and I get y equals -5. So guess what? The middle branch begins right here, and we just get to fill that in, and see, we know the slope. We know the slope, right? If I go 5 units up and 3 over, I get another point. So we know it's got to go through the origin, so I'm going to get a straight line like this. And it's going to continue up here to +5. It's going to continue. There's equals there. It's going to continue to right here. So this gets drawn just like that. And that's a straight line as near as I can draw it. Now what happens here at this branch? Well, this is just y equals 5 for x greater than or equal to 3. So we would put a circle there, but there's already a dot. So all we do is draw a horizontal line like that. Piece of cake. Now how about number 8? This will be our last one for section 2. I'm not going to work this many problems for each section, but these look kind of interesting. It says find a formula for this guy here. Well, what does that look like? Notice that that's 1 and 1. If we come over here, we get -2 and +4. So that's our reference curve, y equals x squared. Now, from 1 to 2, it's just y equals 3. Now, what about this? From 2 on, we're at 2 and 2, 3 and 3, 4 and 4. So, I think this one's not too bad. We're going to have 3 branches, and we have a dot at 1 here. So, we're going to say something like this. The function is equal to x squared for x less than or equal to 1. Now, I've got the equals there because of the dot. Now, what happens between 1 and 2? Well, let's write that. Now, that's going to be a 1 less than. There can't be an equals. But now, notice here there's a dot. So we're going to have x and then less than or equal to to 2. What do we get? Well, we just get the horizontal line, y equals 3. Now, what happens for x greater than 2? See, it has to be greater. There's a circle there. Well, when x is greater than 2, it looks just like the line y equals x. Okay, it's a piecewise defined function. You take it a piece at a time. All right, for section 2.3, we're given a function here, and it says find the domain. Well, all we can go by is what we see here. So I don't like problems like this. It looks like the domain is going to be -3. But now how far do we go this way? Well, notice this arrow here. This arrow means that it goes to infinity in this direction, so that's going to be part of the range. But if I had to guess, and I do have to guess, I would say up to about 4.5. See, I don't know. Does whoever made this out imply that we keep going forever? I have to put down just what I see. Now, for part B, what about the range? Well, we showed that this is -10, and that's -7. So I'm going to guess, and there's no number down here. So I'm going to guess -14 because I can't do anything but guess. Now, this is labeled 20. So, what does the individual mean that made this out? Well, this arrow doesn't go above the 20. So one possibility is this. But in actuality, I don't know, do I? This arrow to me signifies that this keeps going forever, so I think you would be okay putting that. Now, if they wanted this, in my opinion, if they wanted this to be the range, they would not have that arrow and they would put a dot there or something like that. But they've got that arrow there. So all I can do is the best I can. It's either going to be this or this, and I can't do any better. I wish I could. Now, part C, what's f of -2? Well, when x is -2, it looks like y is 20. Let's go over here and do this. When x is 0, it looks like -10. And maybe x is 3. When x is 3, what do you think? When x is 3, I don't know. -5 maybe. I don't really like problems where I have to guess. Okay, now D, what are the intervals where the function's increasing? Well, increasing means as x changes, y increases. As x goes to the right, y increases. So it looks like it's increasing from, say, -3 up to -2, I reckon. And then if you come down here, it looks like it's increasing from 0 to 2. And then maybe from, see, look, we have to guess. I'm going to guess 3.5. And it looks like infinity. Intervals where it's decreasing, well, that would be from -2 to 0, right? And then it looks like it's decreasing from 2 to 3.5. Find all local max values of the function and the x values where they occur. Well, I've got a local max right here. So it looks like a local max is y equals 20 when x equals -2. Do I have any more? Yeah, right here. I also have y equals 0 when x equals +2. There's a little local. Think of the local maxes as a hill. Think of the local mins as a valley. I got a local min of y equals -10 when x is 0. And I've also, now here we've got a guess. I'm going to guess y equals -5 when x is, well, who knows, 3.5, best I can do. H, find all values of x where the y values are 0. Well, all that's asking is where does it cross the x-axis? Find all values of x, so that would be -3, looks like -1, and 2. Find all values of x where the y's are less than 0. Well, if they're less than 0, they're negative. So, geez. How did we write this? We've been saying this was -3. So let's just guess negative 3.2 to -3. And then they're going to be negative from -1 to +2. So from -1 to +2. Now see, the y value is 0 there. It says less than 0, so we cannot include 2. And then it looks like from 2 to 4, the y values are negative. Now, of course, the last part is where are the y values positive? Well, where they're not negative. So -3 to -1, the y values are above the x-axis. And then from 4 to infinity, it looks like. So there's section 2.3. Not a big fan of this. I have to guess at too many values. All right, section 2.6. Let's do a couple of these. Problem 1, it says for each function, list the base function, or the reference function, what we call it in our class. Describe the transformation in words and draw the function by transforming the reference function. Okay, so the reference here, the reference function is f of x equals x squared. And this means what? We're going to go 3 to the right and 4 up. So shift, or you can use slide 3 to the right and then up 4. And then just a little sketch. I like to do this. Here's my reference guy. So I'm going to move it 3 right and 4 up. Piece of cake. Piece of cake. Let's do B. Now here the reference curve is y equals square root of x. Now let's draw what this guy is. This guy looks like this. Okay? So what's happening here? When you replace x with minus x, all it does is reflect it across. So this is just reflected. So when you replace x with minus x, you simply draw its mirror image across the y-axis. Nothing to it. Which one? Let's do one more. Let's do D. Now here the reference curve is going to be, this is a tough one, the reference curve is going to be 1 over x squared. Now that looks like this. Okay. It's asymptotic to the x-axis and the y-axis. Okay? So, this is going to shift everything 5 units to the right. The negative is then going to reflect it across the x-axis. And then the 3 is going to do this. If you pick an x value on the reference, you get a y value. Well, this y value now is going to be 3 higher. So it's going to make it steeper. So let's draw all that out and let's say all that. So it shifts 5 units, right? Reflect. Across y-axis. And then if you see up here, what we get, this is called a vertical stretch. This is going to be then stretched by 3. Okay, so if we try to put all this together in a curve, what I'm going to do is put in dotted my reference curve. So we're going to slide that 5 units right. Let's say this is 5. It's going to be reflected. So see, everything is shifted 5 units, including this y-axis. So I get a new, let me see if I can find something that's a little different color here. So see, my y-axis is shifted also. There's my new y-axis. So the curve is going to be this. This curve is going to be shifted over, so you would have a branch like that and a branch like this. But now it's reflected, so it's going to look like this. Okay, where that's still the x-axis. So it's shifted over 5, everything's shifted over 5 units and then reflected across the x-axis. Okay, now this has got a second page. Let's see if anything's on it of real interest. Yeah, I suspect there'll be something like this on test. You'll be given a graph like this, and here's what we're going to do. In a problem like this, let's find this coordinate. This is 1, 1, 2, 3, 4. So this guy is 1 and 4. This coordinate is 1, 2, 3, 4, 5. So this coordinate is -5 and 2. Okay. Let's just pick one of these. Let's pick this guy right here. Well, we know the 1, it means everything is going to be moved 1 unit up. The x minus 3 means there's going to be a slide of 3 units to the right, 1 unit up, and then all these y values become twice as big. So this is going to become a 4, and that's going to become an 8. So let's do all that. That means this point right here on the x-intercept at -1, 0, that's going to be moved 1 unit up. So it's going to be right there. Does that make sense? Okay, now everything is slid to the right 3 units. So this point moves 1, 2, 3 units over. And again, remember what we said in class. You can do this in any order. I just started here. Now, this point is going to be moved 1 unit up and 3 over. So if we move it 1 unit up, it becomes a 5. Move it 3 over, it becomes a 4. So this guy is now going to live at 1, 2, 3, 4, and 1, 2, 3, 4, 5. So he's going to live right there. But remember that y value is going to be now twice as big. So it's going to be up here somewhere like this. This y value, which is 2, is going to be twice as big. So it's going to be at a 4. Now let's see, this was at -5. If we slide this 3 to the right, it would be at -2. And instead of it being 2, it's going to be at 4. So if we put all this together, we're going to get that. That's that little curvy part right there. And then this little curvy part would be like this. Okay? Now, it's not immensely accurate because the word in the problem was sketch. And there is my sketch. Okay? Now let's go down here to number 4 and determine whether the functions are even, odd, or neither. Well, in both cases, remember, you begin with this. You begin with f of -x. And if it's odd, you get -f of x when you're finished. If it's even, you just get f of x. So let's take A. I'm going to begin, I'm going to begin with f of -x. That's going to be minus x cubed 5 times minus x minus 1. Now negative x, quantity cubed, is minus x cubed. And then this would be minus 5x minus 1. And see, that does not equal minus f of x, and it does not equal f of x. So this one is neither. Let's do C real quick. I begin at f of minus x. That's going to be minus x plus 6 over minus x. Now that's going to be minus x minus 6 over x. And now notice I can factor a negative out, and that becomes x plus 6 over x. Now x plus 6 over x was f of x, so this is minus f of x. So I began with f of minus x and got minus f of x, so this guy here is an odd function. And remember, if it's an odd function, it's symmetric about the origin. An even function is symmetric about the y-axis. Okay, that'll do it. That'll do it for section 2.6. Okay, section 2.7, some composition of functions. Let's just work the first one very quickly. F of x plus g of x. You could see this written like this on the exam. So f plus g evaluated at x means this, and it's not too interesting, is it? It means that. And this just means them multiplied together. This just means them divided. Now, compute the domains. That's pretty easy. The domain of f, well, just look. It's everything except 1/2. So it would be minus infinity to 1/2, union with 1/2 to infinity. And guess what? The domain of g is the same thing. So I guess since the denominators are the same, we could go ahead and add this as x plus 3 to x minus 1. But now let's go on to the composition. So it says, given these two functions, compute the following compositions and state the domains. So right away, the domain of this is all real numbers. It's a polynomial. Now the domain of g is going to be everything but 0. Okay, so let's do f of g, and this should be written like this. I have no control over whoever did this. Now what does this mean? The definition is f evaluated at g of x. So that's going to be f evaluated at 5 over x, right? And that means everywhere in the function f that you have an x, you're going to put in 5 over x. So this is going to be 5 over x squared plus 4 times 5 over x plus 3. So that's 25 over x squared, 20 over x plus 3. Okay, now let's find the domain of this. So we want to find the domain of this particular composition. Well, if you look at the definition, if it was written correctly, this x gets plugged into g first. So that means this x can never be 0. So I'm just going to write here, right above it, x can never be 0. All right. Now we've got to worry. Can this function g generate a number? Can 5 over x ever be a number that gets f into trouble? Well, the answer is no, because f can digest anything. So the domain of f of g, if you want to write it like that, is going to be minus infinity to 0, and then 0 to infinity. Okay, well, let's go down and do C. We want G composed with G, and again, this should be written like this. That bothers me that it isn't. So this is going to be g evaluated at g of x. And this problem, that's going to be g evaluated at 5 of x. Now you got to keep your head on straight here. This means in the function g, wherever you have an x, you're going to put 5 over x. So this is going to be 5 over x, which is going to be 5 times x over 5, or just x. Well, now look, this is kind of cool. This means that the function g is its own inverse. That's kind of a neat thing. What about the domain? Well, this x gets plugged into g, so that means we cannot have 0. Then this is going to be plugged in for x in g. Well, g cannot tolerate a 0, so is it possible for 5 over x to be 0? Does this y value ever become 0? And of course, no. The only way this fraction can be 0 is if the top is 0. That's not possible. Therefore, the domain of g and g composed with itself, is going to be just the domain of g, which is minus infinity to 0, union with 0 to infinity. Okay? Now, number 3, you're given a function in finished form. Let's call it finished form. So you want to find functions f and g so that if you take the composition, if you take f of g of x, you end up with x plus 5 to the 2/3. Now, these are pretty straightforward, but you got to make sure you get these in the right order. So suppose I think it's going to be this. Suppose I think it's f of x is x to the 2/3 and g of x is x plus 5. So if I think that's the way that's going to go, let's see what really happens. We have f of g evaluated at x. That's going to be f of g of x. That's going to be f evaluated at x plus 5. Now that means everywhere in f that you have an x, you're going to put x plus 5. And bingo, that does it. So that's one possibility for this problem. I actually ended up working more than I meant to. And that'll do it for that problem. So that's it for section 2.7. Okay. Now, how to find the inverse? Well, remember, there's just one way to do it. I'm going to replace f of x with y. I'm going to swap x and y. And then I'm going to solve for y. So I've got to move the 9 over. Let's go this way. Now divide by 2. And then take the cube root. So I'm going to get f inverse. Now I'm going to write this as x plus 9 over 2 to the 1/3 power. So that's going to be my inverse. And this algebraic process of swapping x and y just means that the x values here are going to become the y values for the inverse. So these, whatever this is, goes here always. And whatever this is, goes here always. So as soon as you find the domain of the parent or the original function, as soon as you find the domain and range for it, you know the domain and range for the inverse, you just swap them. So I guess I'm being commanded to put my answer here. Okay? So let's do part B. Let's do part B. What's going to be the domain here? The domain is going to be anything but minus 2. I'm sorry, anything but plus 2. So this would be from minus infinity to 2, union with 2 to infinity. Now, what about the range? Well, that's a little difficult to see, isn't it? In fact, that's going to be pretty hard to answer with what we know in section 2.8. But let's just do this. Suppose x is 0, and 0 is okay, isn't it? 0 is okay. We get a negative. So we know we're going to get some negative values. Now, if you come over here and let x equal 20, everything's positive. So there's really no limit to how negative a number can get, and there's really no limit to how big a y value can be. So I'm going to put this. But this is really a tough one because the actual machinery we need to figure this out comes later. And actually, the best way to do it is calculus. But now, look, for the inverse, the range is going to be this. So I can automatically put this down here. And then the domain is going to go right here. Let's go ahead and do this. I'm going to replace g with y. Okay, swap. So this becomes x equals 5y plus 6, y minus 2. Now I want to solve for y. Well, the easiest way to do this is like this, and then cross multiply. That's going to give me x times y minus 2 is equal to 5y plus 6. Now you have to multiply this out, so it's xy minus 2x is equal to 5y plus 6. Now here's our dilemma. I've got y values on each side of the equals. I've got to move all the y's to one side and then everything else to the other. So I think I'm going to move this over here, and I'm going to move the 2x over here. So let's do that. Now factor out the y. Okay. Okay. Now divide through by x plus 5, and that's going to give us y equals 6 minus 2x over x plus 5. And that's going to be my inverse. But now we see that we've got a dilemma, don't we? This isn't accurate because remember, these y values for the original become the x values down here, but clearly we can't have an x equal to minus 5. So that means over here, this is really not accurate. This is going to go from minus infinity to minus 5, and then from minus 5 to infinity. Okay? So that means down here, this is going to be minus infinity to minus 5, and then from minus 5 to infinity. And that's about as good as we can do. That's a tough one, but it would not surprise me if something like that was on the exam. That's a tough one. Really is. Let's see. I want to come over here on the back page and let's look at this one that I've got marked. Now, given this function, now see, we're given the domain. We can come right here and already state this. The domain is going to be minus infinity to minus 3. Okay, now if you use just those x values, what's going to happen? Well, notice that the lead term is x squared. So what's going to be what your book calls the end behavior? See, this is all that matters as x goes to minus infinity. Well, as x goes to minus infinity, a negative squared is positive. So that means if we were trying to sketch this function, we would have a little line like that. As x goes to infinity, the y's go to infinity. Now what happens at negative 3? If we put a negative 3 in, we get 9 minus 18 plus 5. Right? So what's that going to be? Minus 4. Now the question is that the smallest y value? Well, it's kind of hard to say. To say completely, perhaps the only way we can do this now with what we know is to complete the square. So this would be x squared plus 6x plus 9 plus 5 minus 9. So see, this would be x plus 3 squared minus 4. Now, do you recognize this guy? This is going to be our y equals x squared shifted 3 units to the left and 4 units down. So that means that the smallest y value is going to be minus 4. So this is going to go from minus 4 to infinity. Now, it's not that there's an easier way that we just haven't discussed, or maybe you need calculus to do this. Calculus would help. But in general, finding ranges is really difficult. Very, very difficult, generally speaking. But we've got it. So now we know that these range values, these y values, are going to be the x values for the inverse. And these x values for the parent function are going to be the y values here. So let's go through our procedure. The same old thing. We have y equal x squared plus 6x plus 5. And then swap x equals y squared plus 6y plus 5. Now I've got to solve this for y, but I'm going to do this in an unusual way because of that squared there. I'm going to move the 5 over. And then on the right, I'm going to complete the square. Okay, so that's going to give me y plus 3 squared. Well, if I added 9 over here, I have to add 9 over here to balance it. So I get x plus 4. So what has to be done now? We have to take the square root. So y plus 3 is going to be equal to the square root of x plus 4, but we pick up a plus or minus here. Now what's it going to be? Well, if I finish solving this, let's go ahead and do it. I get y is equal to minus 3 plus or minus the square root of x plus 4. Well, look at what the range has to be. For the inverse function, it has to go from minus infinity to minus 3. It has to be negative, doesn't it? It has to be negative y values. Well, the only way it can be negative is if we pick this. Because if we were to pick the plus sign, with these numbers, this is just going to get larger and larger and larger, and it would not take long before there's no negative y values. So the inverse is going to be negative 3 minus the square root of x plus 4. And again, the reason I picked that minus was because these ranges have to be negative. Okay, now let's look at 2 here real quick. If f of x is a one-to-one function, and you're given this, now what does this say? Look over here. What does that say? That says when x equals 5, y equals minus 4. And then look what you're asked to find here. It's almost a trick question. Remember, this says when x... So again, what this means is f of 5 is minus 4. It means that 5 and minus 4 is a coordinate on the graph of this function f. Well, when we find the inverse, we swap x and y. So if 5, negative 4 is a point on the function f, then if we swap x and y, negative 4 and 5 have to be a point on the inverse. So you just swap these numbers. That's what it amounts to. Look at this one. If f inverse of 23 is 8, then f of 8 has to be 23. You just swap them. Piece of cake. Okay, that's going to be it for section 2.8. All right, let's look at section 3.2. It says, list the degree, the sign of the leading coefficient, find the x and y intercepts, and sketch the graph. Very, very good problem, straightforward. Okay, leading coefficient is x to the 4th. So leading coefficient is x to the 4th, right? So what does that mean? Well, as x goes to minus infinity, x is negative, so a negative to the 4th power is positive. And obviously, if x is positive, as x goes to plus infinity, then a positive to the 4th is positive. So this guy's going to go look like this. Now, remember, just come over here. I'm going to draw a little baby coordinate system. We have to find the x and y intercepts. At a y-intercept, x is 0. So to get the y-intercept, we plug 0 in. Well, if x is 0, that means when x is 0, that means the y-intercept is 0, 0. Because when x is 0, you get a y0. Now, what about for the x-intercept? Well, draw yourself an x-intercept. At the x-intercept, y is 0. So look at that. If we do that, now notice here I have a common factor of x squared, right? That's going to leave me an x squared plus 2x minus 63. That's going to be an x squared times... Now the factors of 63 that we want are 9 and 7. The middle term is positive, so this will be x plus 9 and x minus 7. So the x-intercepts are going to be from here, 0, 0. And then from here we have minus 9, 0. And then from this one we have 7 and 0. Okay? Now, sketch this thing. Well, notice one of the roots is 0. It has multiplicity 2. So right here, the curve is just going to kiss or be tangent to the x-axis. At the other two zeros, like minus 9 and 7, they have to be pass-throughs because the multiplicity is 1. So what's going to happen? It's got to go like this. It's got to pass through this 0. It's got to come back up, and it's just going to be tangent. It's got to come back down like this and then pass up like that. So it's got to be doing something of that nature. Okay? It's got to be doing something of that nature. All right, let's go down here and look at C. C looks really tough, but it's an illusion. If you look at this, I've got 1, 2, 3 terms. And each term has a common factor of x minus 4. Okay? If I take an x minus 4 out of the first term, I'm left with minus x squared. If I take an x minus 4 out of this term, I have a 3x. And if I take an x minus 4 out of this term, I have a 4. Now, I want to do one other thing. I want to factor this minus out. And this is going to be, when I factor the negative out, it's going to be x squared minus 3x. And then minus 4. So we had to find the degree. Well, the degree is going to be degree 3, isn't it? So degree 3. Up here, this was degree 4. The lead coefficient was 1 up here. So the degree was 4. Down here, the degree is 3. The lead coefficient is negative 1. We can put negative 1. Okay, now what does that mean? The lead coefficient's minus 1. That means as x goes to minus infinity, well, if you cube a negative number, you get a negative. So it goes like this. Well, if you cube a negative, you get a negative. So I'm sorry. If you cube a negative, you get a negative, but we have a negative out front. Yeah, it's going to go that way. So this is going to be like minus x cubed and stuff. So if x is negative, a negative cubed is negative, and then that negative makes it go to positive. Whew. Now, as x goes to plus infinity, well, a positive number cubed is positive, but that makes it negative. So it's got to go like this. So now, what else happens? Well, we have to investigate just a little more. This, it turns out, factors into x minus 4, x plus 1. So look, here are my, if I write this one more step, x minus 4 squared times x plus 1. So I have a 0 at 4 of multiplicity 2, which means it's just going to be tangent. And then I have a 0 at minus 1 over here. So now, knowing all that, this is what's got to happen. Since this is a multiplicity 1, this is going to be a walkthrough. It's going to come down like this. It has to turn back up. It has to be tangent to the x-axis. And then it has to go like that. Okay? And let's see what's on page 2. I've got C marked here. This is really a neat problem. If there's one like this on the test, they're doing you a big favor, aren't they? They're doing all the work for you just about. So this is going to be an x squared. This term, when you square it, is an x squared, and this is an x. So this is degree 5. The lead coefficient, well, each coefficient is a 1. So the lead coefficient is a 1. And from this, we can read off the x-intercepts. We have an x-intercept at minus 9. We have an x-intercept at what? 4. Yeah. See right there. Now here, if I set this term equal to 0, I get x is plus or minus the square root of 5. So I'm going to have an intercept at minus the square root of 5, and I'm going to have an intercept at plus the square root of 5. So what's going to go on with this thing? Well, what's going to be the y-intercept? Remember, to get the y-intercept, you set x equal to 0. So when I do that, that's 9. If I let x equal 0, then that's minus 5. And if I let x equal 0, that's 16. Holy moly. That's going to be 5 times 16 is 80. And then 80 times 9 is minus 720. Now it's minus because of that. So this thing is way down here. Okay, now it's degree 5. So as x goes to minus infinity, a negative number to the 5th is negative. So it's going to do this. As x goes to plus infinity, a positive number to the power of 5 is positive. So it's going to go off like this. Now, this is the only one that has multiplicity 2. See, this can be factored into x minus the square root of 5 and x plus the square root of 5. See? So these are all multiplicity 1, so they're walkthroughs. So here's what's going to happen. It's going to come up like this. It's got to go through here. It's then got to turn down. It's got to go way down here to minus 720. Holy moly. It's got to go down here. It's going to come up. It's going to pass through this. It's going to come down and then be tangent at 4. So let's see if we can draw that decently. It's going to come up like this, come down, go like this, go up. It's got to come back down to be tangent right there, and then it's going to leave like that. That's a good one. Okay, that'll do it for section 3.2. All right, section 3.3 is long division. The review sheet's like this. I've just copied a couple of problems over onto other papers, so we'll have a little more room to work it. Now, in 2B, it says find the quotient and remainder. Okay. So this is just going to be a long division problem. No big deal. We know how to do this. We just have to be careful. This is x to the 7th. Now there's no x to the 6th term. So I'm going to put one in. Then we have x to the 5th. There is no x to the 4th, so I'll put one in. There's an x cubed. There is no x squared term. Okay. Now, we need an x to the 7th. We have x squared, so we're going to multiply by x to the 5th. Now, this is kind of cool. You got to look at what happens here. When I take x to the 5th times x squared, I get x to the 7th. And then when I take x to the 5th times 2, I get a 2x to the 5th. And notice I'm skipping this guy. Okay? Now we do this, and of course, what do? We change the signs and add. Okay, that gives me 0. That gives me minus 2x to the 5th. It turns out, it looks like we don't need this, but you always want to put them in. Okay, now I've got an x squared. I need x to the 5th, so I'm going to have a minus 2 x cubed. So that gives me a minus 2x to the 5th. And then what am I going to get here? I'm going to get a minus 4x cubed. So if you want to, you can bring this x cubed down here. All right, now what do? Well, we change the sign. Each one of these. And then add. This would be 0. Now this would be 4 and 1, so this is 5x cubed. Now next I need a 5x. So this is going to be a 5x cubed, and then 5x times 2 is going to be a 10x plus a 10x. So I can bring that x down. Okay. We change the signs. We change the signs and add. This will be 0. This will be minus 9x. And then we can bring the 1 down. Now notice the divisor is degree 2 polynomial, and I've got a remainder of degree 1. That means I'm finished. So the directions are to find the quotient and the remainder. So the quotient, let's call it q of x, is x to the 5th minus 2x cubed plus 5x. And then the remainder term is minus 9x plus 1. And that's all there is for that problem. Okay, kind of a neat problem. We put in all these 0 terms, and turns out we didn't need them. But you always want to put them in because generally you do need them. Okay, now I've got one more to look at from section 3.3. This is problem 3. It says, show x equals 2 is a 0 of this polynomial, then find all the other zeros. Well, I want to use the remainder theorem. I want to take and plug 2 in for x. And we know the easiest way to do that is synthetic division. Degree 3, degree 2, degree 1, so there's no missing terms. Okay, got them all in there. Bring the 1 down. 2 times 1 is 2. Now I add and get minus 15. 2 times minus 15 is minus 30. I add and get 50. 2 times 50 is 100. 0. A remainder of 0 means 2 is a 0 of that polynomial. So that means that is 0, and it means x equals 2 is a 0. Now if I bring the 2 over, that means x minus 2 is a factor. So I need to find the other 2 roots. Notice it's a degree 3 polynomial. There's going to be 3 roots. We have to find all the other roots that are real. Now it could be the other 2 roots are complex. We'll just have to see. Now we know that this is going to be the quotient. The original problem was degree 3. We divided by this factor. So this quotient has to be degree 2. So let's call it Q of x. Q of x has to be x squared minus 15x plus 50. Now, does that factor in any way? Well, let's see. The factors of 50, my goodness, there's a whole bunch. But what we want to do is set this equal to 0. And we're lucky in that this does factor, right? This would be x minus 5 and x minus 10. So therefore, the roots are going to be, or the zeros are going to be 2, and then we pick up 5 from here, and then we pick up 10 from here. Now, just what would you have done if you could not have factored it? Well, you would have used the quadratic formula. So let's do that real quick. By the quadratic formula, you change the sign, so you get 15. Put plus or minus. Now inside goes this number squared, which in this case is 225. And then it's minus 4 times the lead coefficient, which is 1 here, times the last coefficient, which is 50, divided by 2 times the lead coefficient. So this would be 15 plus or minus, and this is going to be 225 minus 200. So this is going to be 15 plus or minus 5 over 2. And see, this is 2 numbers. This is 15 plus 5 over 2. That's 20 over 2, which is 10. And then it's going to be 15 minus 5 over 2. Well, that's 10 over 2, which is 5. Others. Okay? Now, problem 4 is a really cute problem. It's a lot of fun. Now, look at what it says. It says, find a polynomial of degree 5 with these zeros. Now, notice there's only 4 zeros. What does it mean to be a 0? That means that x equals minus 6 is a solution. And if I move that over, I get x plus 6 equals 0 as a factor. So one factor is x plus 6. So let's call it p of x. I know one term is going to be x plus 6. Another root or another 0 is minus 1. Now if I move that over, I get that x plus 1 is 0. So I'm going to tack on the x plus 1. I know that 3 is a 0, so x equals 3. So I have x minus 3 equals 0. That's going to be a factor. And finally, x equals 9 is a root. So x minus 9 equals 0 would be a factor. Okay? Now, the issue is, though, it must be degree 5, And if we were to multiply all this stuff together, we would end up with a polynomial of degree 4. So how do we get another power of x? Well, it's really simple. We can pick any of these and give it multiplicity 2. I picked this because that's the easiest. Now that's going to be a degree 5 polynomial. Now here's the question. Is that good enough? Or do I have to multiply all this stuff out? I don't know. If I have to multiply it out, it's going to take me a while. I'm just going to stop right there. That is a polynomial. It is a polynomial of degree 5, and it does have those 4 zeros. Finished. Okay, that's it for 3.3. We have one more section, 3.6, to look at. All right, section 3.6. Let's look at just a couple of problems. It says, find the domain, find the x-intercepts, the y-intercepts, the vertical asymptotes, the horizontal asymptotes, and sketch a mugshot of this thing. Well, I'm going to do part B, and I'm going to write above it and below it. In part B, let's do the easy part first. The domain of f, we can have everything but 4. So the domain then would be minus infinity to 4, and then 4 to infinity. Okay, there's the domain of this guy here. Now, it wants x-intercepts and y-intercepts. And there's the little trick. What happens at a y-intercept? Well, you get a 0 and some y value. So to find a y-intercept, you let x equal 0. Well, just cover them up. If you let x equal 0, you end up with 12 over negative 4. So this is negative 3. So the y-intercept is going to be the coordinate 0 and negative 3. You have 12 over negative 4. Okay, x-intercept. Well, what happens at an x-intercept? Well, you get, of course, some x value, but you get a y of 0. So if I come over here and set y equals 0, let's do it right here. Okay, when can this fraction or any fraction be 0? Well, this can only happen if the top is 0. So that'll give me negative 4. So the x-intercept is going to be at negative 4 and 0. Okay, now let's see if we can sketch this puppy. Now, what's going to be the vertical asymptote? Remember, you get the vertical asymptote from the domain. X equals 4 is forbidden. So x equals 4, let's put it right here. X equals 4 is going to be a vertical asymptote. The function cannot cross this. The function cannot cross this. Whatever the function's doing, it's going to be bending when it gets close. Now for the horizontal asymptote, we're going to cover this Friday, the 4th. What we do is we look at the problem and find the biggest power of x, and then we multiply by its reciprocal. Now see, I'm not doing anything illegal here. 1 over x divided by 1 over x is still 1. But here's what happens. When I take 1 over x times 3x, the x's cancel and I get 3. When I take 1 over x times 12, I get 12 over x. Downstairs, I'll get 1 minus 4 over x. Now remember, you're only ever going to have a horizontal asymptote when the degree of the polynomial part upstairs is the same or smaller than the degree downstairs. Here, both are degree 1. So we're going to have a horizontal asymptote. And the horizontal asymptote is addressing the question of what happens as we go way out left and right. Well, as x goes to minus infinity, or if x goes to plus infinity, you get 12 divided by something that's bigger and bigger and bigger and bigger and bigger. So eventually, these just kind of don't have any value at all. They tend to go to 0. So that means this is going to behave like y equals 3. So that means y equals 3 is a horizontal asymptote. A horizontal asymptote is always y equals. A vertical asymptote is always x equals. Now remember, the horizontal asymptote does not have to exist. See, if this had been 3x to the 5th, there would not be a horizontal asymptote because the degree upstairs is 5, the degree downstairs is 1, so there's no horizontal asymptote. Also, the vertical asymptote is forbidden. The function cannot cross it. It's possible that the function can cross the horizontal asymptote locally. Now, what's going to happen? Well, here's kind of how you do this. Let's look over here. Let's pick a real big x value, like 100. If x is 100, this is 312 over 96. 312 over 96. 312 over 96. That's bigger than 3, isn't it? So that means these things are going to go like this. Okay? Right? Now, let's pick a real negative number, like negative 100. If we put in negative 100, that's going to give us negative 300 plus 12, which is minus 288. And then negative 100 minus 4 is negative 104. So see, that is going to be what? That's going to be less than 3. So that means it's going to do this kind of thing. It's going to approach from down here. See, this is y equals 3. This is less than 3, so it's got to be below it. This was bigger than 3. So this thing is going to go like this. That's my best guess. Now, we can do some further analysis. And the question is, what happens to the graph as we get close to this forbidden value of 4? Well, what you do is you take this. Now, watch this. This is kind of tricky. You take 3x plus 12 times 1 over x minus 4. See, it's the same thing. It's the same thing. But here's the deal. This part makes sense at 4, and this part doesn't. So let's look here. If I'm walking through these numbers, now here's 4. If I'm walking through these numbers are bigger than 4. Now, what do you get when you take a number bigger than 4 minus 4? Well, you get a positive. And here, a number bigger than 4 plugged in is positive. So see, this is a positive times a positive, which means these things go like this. It goes to plus infinity. Now let's walk through here like these numbers. These numbers are smaller than 4. And what do you get when you take a number smaller than 4 and subtract 4? Well, you get a negative. Now, if you're getting near 4, but from this direction, like 3.5, if you put 3.5 in, this is still positive. So this part's positive, this part's negative, which means this part goes to minus infinity. So our best guess, without calculus, our best guess at what happens is that. And that's as good as I can do. So I think you should definitely focus on the domain. Remember how to find y-intercepts and x-intercepts. the vertical asymptote is found from the domain. It's what's forbidden. X equals 4 is forbidden. And then to find the horizontal asymptote, if there is one, you take the biggest power of x in the problem and make it a fraction, 1 over x. If the biggest power had been x cubed down here, this would be 1 over x cubed and 1 over x cubed. Okay? All right. Now, on the second page, it's the same set of directions for this little problem. Okay? Now, the domain, if we look at this, what can we have? See, down here, this is x times x plus 5. So right away, the domain, I'm going to draw a little number line. See, I can't have minus 5, and I can't have 0. So the domain's minus infinity to minus 5, then minus 5 to 0, and then 0 to infinity. Those are the things I can use. Well, I also get the vertical asymptotes, don't I? The vertical asymptotes are x equals 0 and x equals minus 5. Okay? Now, what else did we have to find? X-intercepts and y-intercepts. Okay, now remember how we do that. Remember how we do that. For a y-intercept, x is 0. So if I plug 0 in for x, I get minus 40. And the bottom is 0. That can't happen. That cannot happen because I'm dividing by 0. So that means there is no y-intercept. How about that? Now for an x-intercept, y is 0. So if I set this equal to 0, when can a fraction be 0? Well, only when the top is. Now, luckily, we're very lucky here in that this factors. The factors of 40 which subtract a 3 are 5 and 8. So this is x minus 8 and x plus 5. So that means we're going to have x-intercepts at 8 and, well, look at what it says. Negative 5. But you know what? Look here. Kind of interesting, isn't it? This is x minus 8, x plus 5 in the top, and the bottom is x times x plus 5. Someone's trying to be tricky, aren't they? So see, we can really rewrite f of x as x minus 8 over x. So all of this, oh man, someone's yanking my chain here. This simplifies to this. Took me a while to figure it out. Now let's start all over again. The domain, see, this is now wrong. The domain is going to be everything but 0. There's still going to be no y-intercept. Because remember, at a y-intercept, x is 0. That can't happen. X-intercept. X-intercept is going to be at 8 and 0. Again, you would set this equal to 0, and that can only happen when the top is 0. Okay, vertical asymptote. Yep. X equals 0 or the y-axis. Now what about horizontal? Well, here's what we do. We take x minus 8 over x, and the biggest power of x is 1. So that can be written as 1 minus 8 over x divided by 1. So we have y is equal to this, And this is going to approximate 1 over 1, which is just 1. So the horizontal asymptote is y equals 1. So what is the graph of this thing going to look like now? Well, we have a vertical asymptote at 8, and then a horizontal asymptote at 1. Oh, that's not right. Thinking about something else. We have a vertical asymptote at 0. I'm sorry. Let's designate it like this. This is x equals 0. That's the vertical asymptote. I'll put dots, slashes in here. Then we have an x-intercept over here at 8 equals 8, 0. We have a horizontal asymptote at y equal 1. So what's going to happen here? Well, if we go back and look at this, let's pick a number way out to the right, like 100. 100 minus 8 is 92. So this would be 92 over 100, and that's going to be less than 1. So it's going to approach this thing like this. So my guess, now it's got to go through this, so my guess it's going to look like this. Okay, now let's pick a negative number, like negative 100. This would be negative 108. So negative 108 over negative 100, that's bigger than 1. So this thing, my guess is, goes like that. Whew. What a problem. What a mess. Yeah. Someone was being really cheeky here about that, weren't they? Okay, well, that'll do it. I hope this helps a little bit.